At the smallest scales we can imagine, the universe stops behaving the way we expect. Distances lose their meaning, time begins to blur, and energy itself becomes so concentrated that space can no longer remain calm. Somewhere far beyond atoms, far beyond particles, there exists a quiet boundary written into the laws of nature, a limit not imposed by technology, but by reality itself. Tonight, we rest our attention on that boundary, and on a question that seems simple, yet reaches deeper than almost any other. Why no experiment, no matter how ambitious, can ever reach the Planck energy? If this quiet journey brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like, a soft tap on subscribe, or a few quiet words of feedback help keep these stories drifting gently through the night. Thank you for being part of this still corner of the universe. Now, let's begin with the first truth. Part 1. What does it mean to reach the ultimate energy? At the edges of modern physics, energy is not just fuel or motion. It is the substance that shapes reality itself. When scientists speak of Planck energy, they are not describing a machine setting or a laboratory goal, but a threshold where energy becomes dense enough to rewrite the structure of space and time. It is the point where our familiar ideas of measurement begin to soften, and where the universe quietly refuses to be pushed any further. To understand why this idea matters, it helps to let your perspective drift for a moment. Think about energy in the way you encounter it every day, the warmth of sunlight on your skin, the gentle hum of electricity through a wire, the motion of your breath as air flows in and out. In these familiar forms, energy feels tame, measurable, cooperative. It follows rules we can test, store, and control. Physics at these scales feels reliable and calm. But as scientists began probing deeper into the fabric of reality, they discovered that energy is not merely something that moves through space, it is something that shapes space. According to Einstein's equations, energy and mass tell space-time how to curve. This means that energy is not just acting within the universe, it is actively sculpting the stage on which all events unfold. At low energies, this curvature is so gentle that space appears flat and time flows smoothly. But as energy increases, its influence grows stronger. The geometry beneath reality begins to bend. Paths that were once straight become curved. Clocks begin to tick at different rates. What feels solid and dependable at human scales becomes flexible at cosmic ones. Planck energy represents the point where this flexibility can no longer be ignored. The value itself is almost impossible to picture. Roughly 1019 giga-electron volts, it is many trillions of times more energetic than the particles accelerated in the most powerful machines humanity has ever built. The Large Hadron Collider, a 27-kilometer ring buried beneath the border of France and Switzerland, reaches energies that already stretch engineering to its limits. And yet, those energies are still unimaginably small compared to the Planck scale. This is not a small step further. It is a leap across an abyss. Why does this particular energy matter so much? Because it marks the point where two pillars of modern physics collide. Quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which governs gravity and the structure of space-time, both work beautifully in their own domains. But at Planck energy, they are forced into the same room, and they no longer agree. Quantum mechanics tells us that uncertainty is fundamental. You cannot know both the position and momentum of a particle with perfect precision. Reality at its core is fuzzy. General relativity, on the other hand, treats space-time as smooth and continuous, bending gracefully under the influence of mass and energy. At ordinary scales, these descriptions coexist peacefully. At Planck energy, they clash. To reach such energy in a tiny region of space would mean concentrating an extraordinary amount of energy into an extraordinarily small volume. Quantum mechanics allows this only fleetingly, through fluctuations. Gravity responds instantly, curving space so intensely that the region threatens to collapse in on itself. The attempt to probe deeper becomes self-defeating. The more precisely you try to measure, the more violently reality pushes back. This is why physicists speak of the Planck scale not as a destination, but as a boundary. Imagine trying to examine the surface of a calm lake by throwing stones into it. At first, small ripples reveal the texture of the water, but throw a stone that is too large and the surface explodes into chaos. The water is no longer something you can observe clearly. You have overwhelmed it. At Planck energy, space-time behaves in much the same way. The probe becomes too disruptive. Observation turns into destruction. There's also a deeper implication here, one that feels almost philosophical in its quietness. Throughout the history of science, every limit has eventually fallen. Better instruments replaced old ones. New theories expanded old frameworks. But the Planck energy does not behave like a temporary barrier. It is woven from fundamental constants, the speed of light, Planck's constant, and the gravitational constant. These are not technological limits. They are properties of the universe itself. In other words, this boundary is not waiting for us to cross it. It is telling us something about how reality is constructed. When physicists calculate Planck energy, they are effectively asking a profound question. At what point does energy become so intense that space-time itself can no longer remain a passive backdrop? The answer is not arbitrary. It emerges naturally from the equations. It is the energy scale at which gravity becomes as strong as all other forces combined, and where the smooth fabric of space-time is expected to break into something granular, restless, and unstable. Some physicists describe this as space-time foam. Others avoid metaphors altogether, acknowledging that our language fails us here. What matters is that at this scale, the concepts of distance and duration may lose their meaning. You can no longer talk about here and there or before and after in the way we intuitively understand them. This does not mean the universe becomes chaotic in the everyday sense. It means our current descriptions stop working. There is something almost soothing in this realization. The universe is not hiding its deepest secrets out of malice or indifference. It is simply structured in such a way that certain questions cannot be answered by force. No matter how much energy we pour into an experiment, the act of pushing harder eventually changes the nature of what we are trying to observe. This is why Planck energy is sometimes described as the ultimate energy, not because it is the highest number we can write down, but because it marks the end of a particular way of knowing. Beyond it, new principles must take over. New forms of understanding must emerge. For now, those forms remain incomplete. Theories of quantum gravity attempt to bridge the gap, to describe how space-time behaves when quantum uncertainty and gravitational curvature are equally strong. But without experimental access to Planck energies, these theories remain guided by mathematics and consistency rather than direct observation. And yet, even without reaching this scale, its presence shapes everything we know. The early universe, in its first fleeting instance, likely existed at energies close to the Planck regime. The large-scale structure of galaxies, the uniformity of cosmic radiation, and the arrow of time itself may all carry faint imprints of physics that operated near this boundary. So when we ask what it means to reach the ultimate energy, we are really asking something quieter. We are asking where the universe draws the line between what can be explored and what must be inferred. We are asking how knowledge itself is shaped by the structure of reality. As you rest here, breathing slowly, there is no need to chase these answers. It is enough to recognize that the universe has depth not just in space, but in scale. That beneath the calm surfaces we experience lies a layered reality, one that becomes stranger and more delicate the closer we look. And as we continue this quiet journey, one question naturally follows. If energy is the key to seeing smaller and deeper, why does every step inward demand so much more of it? Part 2. Why seeing smaller always requires more energy. Every time humanity has tried to look deeper into matter, the rule has remained the same. To see something smaller, you must use something more energetic. Shorter wavelengths, faster particles, stronger collisions, this simple relationship has guided microscopes, particle accelerators, and telescopes alike. But as this journey inward continues, the energy required rises not gently, but explosively, hinting that the universe may be guarding its smallest secrets. To understand why this rule exists, It helps to begin with something familiar and quiet. Light. The same soft illumination that fills a room, that traces the edges of objects, that allows you to see the world without effort. Light behaves as a wave, and like all waves, it has a wavelength, a gentle spacing between its crests. That spacing determines how much detail it can reveal. A wave can only resolve structures larger than itself. Anything smaller is smoothed over, hidden beneath the rhythm of the wave. Visible light has wavelengths measured in hundreds of nanometers. At that scale, atoms are far too small to be seen. No matter how perfect a glass lens becomes, no optical microscope can reveal individual atoms. The limitation is not craftsmanship, it is physics. To see finer details, the wavelength must shrink, and to shrink a wavelength, energy must increase. This realization marked a turning point in science. When physicists reached the limits of visible light, they did not give up. They changed the tool. Electrons, once thought of purely as particles, were revealed by quantum mechanics to behave like waves as well. Their wavelength depends on their momentum. Accelerate an electron, give it more energy, and its wavelength shortens. Suddenly, the atomic world became visible. Electron microscopes transformed biology, chemistry, and material science. Viruses, crystal lattices, even individual columns of atoms emerged into view. But the rule did not disappear. It only moved deeper. To see smaller still, electrons had to be accelerated to higher and higher energies. Each improvement demanded more power, more precision, more control. The same pattern unfolded in particle physics. To explore the structure of the atomic nucleus, scientists fired particles at one another at enormous speeds. Early experiments revealed protons and neutrons. Later, even higher energy collisions revealed quarks inside them. Each layer of discovery required a dramatic increase in energy. Each step inward was harder than the last. This is not coincidence. It is built into the mathematics of waves. Shorter wavelengths mean higher frequencies. Higher frequencies mean higher energies. This is true for light, for electrons, for any quantum object used as a probe. The universe does not allow gentle shortcuts at small scales. Fineness of detail demands intensity. There is something deeply consistent about this. Nature does not reveal its smallest structures passively. It requires interaction. To learn what something is made of, you must disturb it. The deeper you wish to see, the more severe that disturbance becomes. At first, this disturbance is manageable. Atoms can survive gentle probing. Nuclei can survive collisions at modest energies. But as we push further, the act of observation itself becomes violent. Particles shatter. Energy converts into new forms of matter. The experiment no longer simply observes structure, it creates it. This is where the journey inward begins to feel different. At very high energies, collisions do not just reveal smaller pieces, they produce entirely new particles. Energy becomes mass, just as Einstein predicted. The vacuum itself becomes active, spawning short-lived particles that exist only for fractions of a second. The deeper you look, the less stable the picture becomes. And still, the energy requirement continues to rise. The reason it rises so quickly lies in how space itself responds to energy. At everyday scales, space is forgiving. You can pour energy into a system without changing the geometry of the world around it. But at extreme concentrations, energy begins to curve space-time. Gravity, normally the weakest of the fundamental forces, grows stronger as energy density increases. This introduces a quiet tension. To see smaller, you must localize energy into a smaller region. But localizing energy strengthens gravity. At some point, the gravitational effect of your probe becomes impossible to ignore. The very act of focusing energy begins to reshape the region you are trying to study. This is not a technological problem, it is a physical one. Imagine trying to read fine text by pressing your face closer and closer to the page, only to find that the act of pressing crumples the paper. The closer you get, the more you distort what you are trying to see. At extreme energies, space-time behaves like that fragile page. It cannot remain flat under the pressure. As physicists calculate what happens when energy is concentrated beyond a certain threshold, they find that gravity would overwhelm everything else. The region would collapse into a black hole. Information would be sealed away behind an event horizon. No signal could escape. The attempt to see smaller would end in silence. This is why the energy required to probe smaller scales rises explosively. The universe is not merely demanding better tools, it is enforcing a balance. Beyond a certain point, increased energy no longer grants access, it removes it. There is a strange elegance in this. The same principle that allows us to explore the cosmos also limits our intrusion into its deepest layers. Energy opens doors, but only up to a point. Beyond that, it closes them. This helps explain why the Planck scale looms so large in theoretical physics. It is the scale at which the wavelength needed to probe space-time itself becomes so small that the energy required would inevitably create a black hole. The probe disappears. The question collapses into the geometry of space. From this perspective, the rising energy requirement is not a challenge to overcome, but a message to listen to. It tells us that space-time is not an infinitely divisible backdrop. It has structure. It resists being examined too closely. As you sit quietly with this idea, there is no urgency to resolve it. The history of physics is filled with moments like this, where a limit revealed not failure, but direction. The impossibility of building perpetual motion machines taught us about energy conservation. The impossibility of exceeding the speed of light taught us about relativity. The explosive rise in energy required to see smaller may be teaching us something similar, that the universe is layered, not infinitely zoomable, that below a certain scale, different rules apply. For now, scientists continue to explore with creativity rather than brute force. They look for indirect signatures. They study cosmic relics from the early universe. They refine theories that remain consistent even without direct tests. The journey inward has not ended. It has simply changed pace, and as this part of the story gently closes, one question remains suspended in the quiet. If energy curves space and hides what lies beneath, what happens when energy becomes gravity itself? Part 3. When energy becomes gravity, energy and mass are not separate things. Einstein showed us they are different expressions of the same substance. As energy increases, so does gravity. At ordinary scales, this gravity is imperceptible, but when energy is forced into an impossibly tiny region, gravity awakens. It begins to curve space itself, turning observation into influence and measurement into distortion. To feel the weight of this idea, it helps to begin with something gentle and familiar. Gravity, as you experience it, feels steady and predictable. It keeps your body resting against the earth. It guides falling rain, drifting leaves, and the slow motion of tides. At human scales, gravity is quiet. It does not announce itself with drama. It simply holds. For centuries, gravity was understood as a force between masses. Isaac Newton described it as an invisible pull acting across distance, a rule that explained falling apples in planetary orbits with remarkable accuracy. For everyday life, this description worked perfectly. But as physicists began to explore deeper layers of reality, they discovered that gravity was not quite what it seemed. In Einstein's view, gravity is not a force at all. It is a consequence of geometry. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Objects fall not because they are pulled, but because they follow the straightest possible paths through a curved landscape. This shift in perspective changed everything. What matters here is that energy, not just mass, contributes to this curvature. Light bends space-time, radiation bends space-time. Any concentration of energy, no matter its form, shapes the geometry around it. At low energies, this effect is so small that it goes unnoticed, but it is always there, quietly accumulating. Now imagine compressing energy into a smaller and smaller region. At first, nothing dramatic happens. The curvature increases, but gently. Clocks tick slightly slower. Paths of particles deviate almost imperceptibly. These effects have been measured and confirmed countless times, from GPS satellites correcting for relativistic time dilation to observations of light bending around massive stars. But this calm does not last forever. As energy density rises, space-time responds more dramatically. The curvature grows steeper. The geometry becomes tighter. Eventually, the equations predict a critical point where space-time can no longer support itself in a stable form. The curvature becomes so intense that it closes in on itself, forming an event horizon. A black hole is born. What is striking is that this outcome depends not on what the energy is made of, but on how concentrated it is. A black hole does not care whether its mass came from collapsing stars, intense radiation, or hypothetical particle collisions. If enough energy is packed into a small enough volume, gravity takes over completely. This realization reshapes how physicists think about probing the smallest scales of reality. When scientists try to examine tiny distances, they must use probes with very short wavelengths. Short wavelengths require high energy. High energy concentrated into small regions inevitably increases gravitational effects. At some point, the gravitational influence of the probe itself can no longer be ignored. This is where observation turns inward on itself. The act of measuring becomes inseparable from the act of altering. The experiment no longer reveals an underlying structure. It reshapes the space-time it seeks to explore. The deeper you try to look, the more you bend the very fabric you are trying to examine. This is not a technical limitation, it is a fundamental one. The idea that energy becomes gravity is not an abstract curiosity. It has been tested in subtle ways. Even light, which has no rest mass, is affected by gravity and contributes to it. Experiments have shown that beams of light gravitate, albeit weakly. In extreme astrophysical environments, such as near-neutron stars and black holes, radiation pressure and energy density play a crucial role in shaping spacetime. In the early universe, this relationship dominated everything. Just after the Big Bang, energy densities were so high that gravity governed the expansion of the cosmos itself. Spacetime was not a passive container. It was dynamic, evolving, responding directly to the energy it contained. This connection between energy and gravity also explains why gravity becomes dominant at extreme scales, even though it is the weakest force at ordinary ones. The other fundamental forces operate within spacetime. Gravity defines spacetime. When energy densities rise high enough, geometry itself becomes the central player. There is something quietly profound in this. The universe does not allow infinite concentration. It resists being compressed beyond a certain point. When pushed too far, spacetime reacts by time, sealing regions away, hiding information behind horizons. From this perspective, black holes are not anomalies. They are natural outcomes of energy and gravity in balance. As you breathe slowly, consider the stillness of this idea. The universe is not fragile, but it is structured. It has rules that preserve consistency. One of those rules is that energy cannot be localized without consequence. The tighter the focus, the stronger the curvature. This is why the Planck scale emerges so naturally from the equations. It is the point where quantum uncertainty and gravitational curvature become equally important. Quantum mechanics demands that energy fluctuates. Gravity demands that energy curves space. At small enough scales, these demands collide. Physicists sometimes describe this as space-time becoming restless. Tiny regions flicker with fluctuations, momentarily forming microscopic black holes that appear and vanish almost instantly. Whether this picture is literal or metaphorical remains uncertain. What is clear is that the smooth space-time of everyday experience cannot survive unchanged at these scales. The deeper lesson is not one of frustration, but of humility. When energy becomes gravity, the universe reminds us that observation has limits. Not because knowledge is forbidden, but because knowledge itself is bound to interaction. To see is to touch is to change. This challenges the classical idea of a detached observer. At extreme energies, there is no such thing. The observer is part of the system. Measurement is participation. And yet, even here, physics does not fall silent. It becomes more careful. Theories of quantum gravity attempt to describe how space-time behaves when it is no longer smooth. Some suggest space-time is made of discrete units. Others propose additional dimensions hidden from direct view. All are attempts to reconcile the simple truth that energy shapes geometry even at the smallest scales. For now, these ideas remain untested, not because they are unimportant, but because the universe has placed a quiet boundary around direct experimentation. The energy required to probe these regimes would collapse the very stage we need to stand on. As this part of the journey comes to rest, one thought lingers gently. If energy curves space and creates horizons that hide what lies beneath, then perhaps the deepest layers of reality are not meant to be seen directly, but understood through their echoes. And as we continue forward, one question naturally rises. If gravity seals information away, what exactly is hidden at the smallest possible scale of space itself? Part 4. The quiet meaning of the Planck scale. The Planck scale is not a place you can point to on a map. It is a ratio born from the fundamental constants of nature: Planck length, Planck time, Planck energy. Together, they describe a regime where space no longer behaves like a smooth fabric, but like something restless and granular. Here, the universe is not continuous. It flickers. To appreciate what this means, it helps to slow your thoughts and let go of ordinary intuition. We are accustomed to thinking of space as something that can always be divided further. A meter becomes a centimeter becomes a millimeter, and so on without end. This assumption feels natural because at every scale we encounter in daily life, space appears smooth and uninterrupted. But physics has taught us that intuition is shaped by scale. What feels continuous at one level can dissolve into structure at another. Air feels like a smooth, invisible substance until you zoom in far enough to see individual molecules in constant motion. A solid table feels immovable until you realize it is mostly empty space, a lattice of atoms vibrating quietly in place. The Planck scale asks whether space-time itself might follow the same pattern. Max Planck did not set out to discover a boundary of reality. At the turn of the 20th century, he was simply trying to understand how energy is emitted and absorbed. In the process, he introduced a constant, now known as Planck's constant, that revealed energy comes in discrete packets. That single insight opened the door to quantum mechanics. When Planck's constant is combined with the speed of light and the gravitational constant, something unexpected emerges. Natural units of length, time, and energy appear on their own, without reference to any human-made measurement. These are the Planck units. They are not arbitrary. They are what the universe itself defines as meaningful. The Planck length, about 1.6 × 10^35 meters, is unimaginably small. To place it gently into perspective, if you were to magnify a proton until it was the size of the observable universe, the Planck length would still be smaller than a grain of sand within it. It is not small in a practical sense, it is small in a conceptual one. The Planck time is equally elusive. It represents the time it takes light to travel one Planck length, about 5.4 × 10^44 seconds. At this scale, the idea of duration itself becomes difficult to define. Events no longer flow smoothly from one to the next, they blur. The Planck energy ties these ideas together. It is the energy required to probe distances as small as the Planck length. And it is here that the calm picture of space-time as a smooth stage begins to break down. Physicists believe that below this scale, space-time cannot be treated as continuous. The equations that describe gravity and quantum mechanics stop agreeing. Predictions lose clarity. Geometry itself becomes uncertain. Space may fluctuate wildly, forming tiny distortions that appear and vanish almost instantly. This is what some have called quantum foam, a restless background where space-time is constantly bubbling, folding, and reconnecting. Not violently in the everyday sense, but subtly, ceaselessly, beneath everything else. It is important to say this quietly and carefully. Quantum foam is not something we have observed directly. It is a concept that arises when we push our current theories as far as they can go. It is a signpost, not a photograph, but it carries meaning nonetheless. The Planck scale marks the point where our usual descriptions lose their authority. Distance, time, and even causality may no longer behave the way we expect. The familiar language of here and there begins to falter. Before and after blur into something more abstract. This does not mean the universe becomes chaotic or lawless. It means that different rules may apply. Rules we have not yet fully uncovered. There is something almost meditative about this boundary. For centuries, science advanced by assuming that nature could always be divided, measured, and reduced. The Planck scale gently suggests that reduction has a limit, that there may be a smallest meaningful unit of space and time, not because of human weakness, but because of how reality itself is built. Some approaches to quantum gravity take this idea literally. They propose that spacetime is composed of discrete units, like pixels on a screen. Others suggest networks of relationships where geometry emerges from deeper connections rather than existing independently. In these views, space is not fundamental, it is emergent. If this is true, then the smooth spacetime you experience is not a basic ingredient of the universe. It is an average, a large-scale illusion created by countless tiny interactions beneath the Planck scale. This idea can feel unsettling at first, but it also carries a quiet comfort. It suggests that the universe has depth not just outward into space, but inward into structure. That beneath the calm continuity of experience lies a subtle architecture holding everything together. The Planck scale also helps explain why certain questions remain unanswered. Why can't we measure smaller distances directly? Why does gravity resist quantization in the same way as other forces? Why does space-time itself seem to evade microscopic inspection? Because at the Planck scale, the tools we use to ask questions become part of the answer. The act of measurement disturbs the system too strongly. Energy curves space, probes collapse into horizons. The universe responds not with data, but with limits. And yet, those limits are informative. They tell us where our current frameworks end. They guide the search for new ones. In the early universe, conditions may have briefly reached this regime. In the first instant after the Big Bang, spacetime itself may have emerged from a Planck scale reality. Whatever laws governed that moment left faint imprints on everything that followed. The large-scale structure of the cosmos, the uniformity of cosmic radiation, even the arrow of time may carry echoes of physics born at this scale. Today, we cannot recreate those conditions, but we can listen for their whispers. There is a poetic restraint in how the universe reveals itself. It offers clarity, at scales where life can exist and curiosity can thrive. And at the deepest levels, it asks us to slow down, to accept uncertainty, to replace force with patience. As you rest here, letting these ideas drift gently, there is no need to resolve them. The Planck scale is not a problem to be solved in a single lifetime. It is a reminder that understanding does not always mean access, that mystery is not failure, but invitation. And as we continue this quiet journey, another question begins to take shape. If spacetime itself flickers at the smallest scales, what happens when we try to treat it as smooth anyway? Part 5. Why spacetime cannot stay smooth forever. At human scales, space feels calm and unbroken. Even at atomic scales, it remains predictable. But theoretical physics suggests that as distances shrink toward the Planck length, spacetime begins to fluctuate violently. Tiny distortions appear and vanish. Geometry itself becomes uncertain. The quiet stage on which physics unfolds starts to tremble beneath its own rules. To understand why this happens, it helps to begin with the illusion of smoothness. When you run your hand across a wooden table, it feels solid and continuous. But if you could zoom in far enough, that smooth surface would dissolve into a lattice of atoms separated by vast emptiness. What once felt seamless becomes granular. What once felt still becomes alive with motion. Spacetime, physicists believe, may follow the same pattern. At large scales, spacetime behaves beautifully. Einstein's equations describe its curvature with extraordinary precision. Planets follow predictable orbits. Light bends gently around stars. Time flows steadily enough for clocks to agree, at least approximately. Everything feels stable, reliable, and mathematically elegant. But this calm depends on scale. General relativity treats spacetime as a smooth, continuous fabric. It assumes that geometry can be defined at every point, no matter how small. This assumption works remarkably well across vast distances and enormous masses, but it was never tested at the smallest possible scales, and when physicists attempt to extend it there, the equations begin to unravel. Quantum mechanics enters with a very different message. At small scales, uncertainty is unavoidable. Energy fluctuates, fields jitter. Nothing remains perfectly still, even in apparent emptiness. The vacuum itself seethes with activity, particles appearing and disappearing in fleeting moments, allowed by quantum uncertainty. As long as spacetime is treated as a passive backdrop, these fluctuations are manageable. But spacetime is not passive, it responds to energy. And at tiny scales, quantum fluctuations in energy become significant. This is where smoothness begins to fail. Imagine trying to draw a perfectly straight line on water. From a distance, the surface looks flat, but up close, ripples and waves make straightness impossible. At the Planck scale, spacetime resembles that restless surface. Quantum fluctuations inject energy into tiny regions, and gravity responds by curving space in response. The result is a feedback loop. Energy fluctuates, geometry bends. The bending alters how energy behaves. The calm fabric begins to ripple. Physicists sometimes describe this as space-time foam, a term meant to evoke motion without implying chaos. In this picture, space-time at the smallest scales is not smooth but frothy, filled with transient distortions that constantly form and dissolve. Tiny regions may momentarily pinch off, reconnect, or fold in on themselves. This does not mean spacetime is tearing apart in any dramatic sense. These fluctuations are incredibly small and incredibly brief, but they are enough to undermine the idea of a well-defined geometry at every point. The smoothness we experience is an average. Just as a calm sea appears flat from afar while hiding turbulence below, spacetime appears continuous at large scales while hiding restless structure beneath. The equations of general relativity work because they describe this average behavior. But averages break down when you zoom in too far. This realization marks a profound shift. It suggests that spacetime is not fundamental in the way we once believed. It may be emergent, arising from deeper processes that only reveal themselves when smoothness dissolves. One way to see this is to consider measurement itself. To define a distance, you need a ruler. But at extremely small scales, any ruler you use must carry enough energy to probe that distance. That energy, in turn, distorts spacetime. The act of measuring changes the geometry you are trying to define. This is not a flaw in technique. It is a reflection of how spacetime responds to energy. As you try to define smaller and smaller distances, uncertainty grows. At the Planck scale, uncertainty becomes dominant. Geometry itself becomes probabilistic. Distances fluctuate, time intervals lose sharp definition, the very notion of a fixed space-time background evaporates. This is why many physicists believe that space-time cannot remain smooth forever. Smoothness is a large-scale approximation, not an eternal truth. Different approaches to quantum gravity attempt to describe what replaces smooth space-time. Some suggest that spacetime is made of discrete units, like atoms of geometry. In these models, smoothness emerges only when many such units are considered together. Others propose that spacetime arises from networks of quantum information, where geometry is a secondary effect rather than a primary ingredient. What all these ideas share is a rejection of infinite divisibility. They agree that at some point, the classical picture of spacetime must give way to something else. This idea also helps explain why gravity has been so difficult to unify with quantum mechanics. Quantum theories are built on fixed backgrounds. Particles move through space and time. But if space and time themselves fluctuate, the foundation shifts. The rules that work so well for particles begin to wobble when the stage itself is uncertain. There is something quietly humbling in this. For centuries, physics sought certainty through precision, smaller errors, finer measurements, tighter equations. The Planck scale suggests that certainty itself has limits, not because the universe is careless, but because it is structured in a way that resists infinite refinement. As you sit with this thought, it may feel unsettling at first, but there is also comfort here. The universe does not collapse into chaos at small scales. It simply operates under different principles that preserve consistency without relying on smoothness. Even now, the smooth space-time of everyday experience remains intact. These fluctuations are confined to scales far beyond direct perception. Your body, your breath, the quiet passing of time around you are unaffected. The trembling stage lies far beneath, hidden by distance and scale. Yet its existence shapes everything above it. Black holes, the early universe, and the ultimate limits of measurement all trace their behavior back to this failure of smoothness. The reason we cannot probe arbitrarily small distances is not merely a lack of power, but the instability of space-time itself. Push too hard, and the geometry responds in ways that conceal rather than reveal. In this sense, space-time protects its own structure. There is a poetic restraint in this protection. The universe allows complexity, life, and understanding to flourish at scales where smoothness holds. And at scales where smoothness breaks, it gently closes the door, not with violence, but with uncertainty. As this part of the journey settles, one thought remains softly unresolved. If space-time trembles at its foundations, if smoothness is only an illusion of scale, then what truly lies beneath that trembling surface? And as we move forward, that question will guide us deeper still. Part 6. How black holes block our curiosity. There is a point where adding more energy no longer reveals more detail. Instead, it hides it. Concentrate enough energy into a small enough region, and gravity seals it off behind an event horizon. A black hole forms. No information escapes. The act of looking creates a boundary you cannot see past, a cosmic reminder that observation itself has limits. At first, this feels counterintuitive. For centuries, progress in science followed a simple rhythm. If something was unclear, we looked harder. If detail was missing, we increased resolution. Stronger lenses, brighter light, faster particles. Again and again, effort translated into understanding. The universe seemed to reward persistence, but black holes quietly break this pattern. A black hole is not defined by what it contains, but by what it hides. Once an event horizon forms, the details of what lies inside are no longer accessible to the outside universe. Matter, radiation, even information itself becomes trapped. The boundary does not shimmer or glow. It does not announce its presence. It simply marks a point of no return. This boundary is not a wall in space, it is a limit in time. Once crossed, all possible futures lead inward. What matters for our story is how easily this boundary can form when energy is concentrated too tightly. You do not need a collapsing star, you do not need cosmic scales. In principle, any form of energy, if compressed enough, can produce an event horizon. Gravity does not care about origins, it responds only to density. This is where curiosity meets resistance. To see smaller details, physicists increase energy. Higher energy means shorter wavelengths. Shorter wavelengths probe smaller regions. But energy has weight, not metaphorically, but physically. As energy increases, so does the curvature of space-time around it. Gravity strengthens quietly at first, then decisively. At some critical point, the region you are trying to study collapses under its own gravitational influence. The probe disappears behind an event horizon of its own making. The experiment ends not with clarity, but with silence. This is not speculation. It follows directly from general relativity. Physicists can calculate the Schwarzschild radius, the size of the event horizon associated with a given amount of energy. As you try to localize energy into a region smaller than this radius, gravity wins. The region becomes causally disconnected from the rest of the universe. No signal can escape to tell you what happened inside. In other words, the universe responds to excessive curiosity by closing the door. This has profound implications. It means there is a fundamental limit to how finely we can probe space-time. Not because our tools are insufficient, but because the act of probing creates the very obstacle that blocks us. Black holes, in this sense, are not exotic exceptions. They are natural consequences of energy and gravity interacting. They are the universe's way of enforcing consistency. There is something quietly elegant about this enforcement. The same laws that allow black holes to exist also prevent paradoxes. Without event horizons, extreme concentrations of energy could lead to inconsistencies, infinite densities exposed to the outside world, breakdowns in causality. The horizon preserves order by hiding what would otherwise destabilize the structure of reality. From the outside, black holes are remarkably simple. They are described by just a few properties: mass, charge, and spin. Everything else is erased. The detailed history of what fell in is lost to the observable universe. This simplicity is not a lack of complexity, but a form of protection. As you rest with this idea, notice how different it feels from everyday experience. In daily life, boundaries are physical. Walls can be touched, doors can be opened, but the boundary of a black hole is woven into space-time itself. You cannot stand beside it. You cannot cross it and return. It is not a vital place so much as a condition, and this condition appears precisely when we push energy too far. This is why black holes play such a central role in discussions of the Planck scale. If we attempt to probe distances as small as the Planck length, the energy required would be so extreme that a microscopic black hole would form. The probe would vanish. The information would be hidden. The experiment would defeat itself. The universe, it seems, does not allow naked access to its smallest scales. There is a subtle philosophical shift here. Knowledge is no longer limited only by imagination or engineering. It is constrained by the structure of reality. Some questions cannot be answered by direct inspection because the act of inspection alters the system beyond recognition. This does not mean the questions are meaningless. It means they must be approached differently. Physicists have learned to study black holes not by looking inside them, but by observing their effects. How they bend light, how they merge and ripple space-time with gravitational waves, how they influence their surroundings. In the same way, the deepest layers of space-time may only be accessible through indirect clues. This approach requires patience. It replaces force with listening. Even the information paradox, the question of whether information truly disappears inside black holes, reflects this tension. Quantum mechanics insists that information must be preserved. General relativity seems to allow it to be hidden forever. Resolving this paradox has driven decades of research, leading to ideas like holography, where information about a volume of space may be encoded on its boundary. If true, this would mean that the event horizon is not just a barrier, but a ledger, a surface that quietly records what passes through it, even if that record is inaccessible in ordinary ways. Again, the universe does not shout its answers, it whispers them through constraints. As you breathe slowly, let this settle. The universe allows exploration, but not domination. It invites curiosity, but not intrusion beyond certain limits. When energy becomes too intense, gravity intervenes, not as an enemy, but as a guardian of structure. Black holes remind us that seeing is not the same as knowing, that some truths cannot be reached by shining brighter light or building larger machines. They must be inferred, respected, approached with humility. And yet, even in this limitation, there is wonder. The same physics that blocks our curiosity also creates some of the most beautiful phenomena in the cosmos. Black holes shape galaxies, power quasars, and generate ripples in spacetime that we can now detect across billions of light years. They are not voids of meaning, they are anchors of mystery. As this chapter draws to a quiet close, one question lingers gently in the dark. If black holes arise naturally when energy is pushed too far, then how large would our tools need to be to even attempt such an experiment? And as we move onward, that question leads us to consider scale itself. Part 7. Why no accelerator can be big enough. It's tempting to imagine solving this problem with scale. Bigger machines, longer tunnels, more power. But the energy required to reach the Planck regime is so extreme that even an accelerator spanning the galaxy would fall short. This is not a failure of engineering. It is a reflection of how quickly energy requirements rise as we chase smaller distances. Human history is filled with moments where limits dissolved under persistence. When microscopes reached their limits, we invented new ones. When rockets could not escape Earth, we built stronger engines. When particles refused to reveal their secrets, we accelerated them harder. This pattern has shaped our expectations. When confronted with a boundary, our instinct is to push. In particle physics, this instinct has been remarkably successful. Early accelerators fit inside rooms. Later ones stretched across campuses. Today, the Large Hadron Collider forms a ring 27 kilometers in circumference, cooled to temperatures colder than deep space, guided by thousands of superconducting magnets. It accelerates protons to energies unimaginable just a century ago. And yet, in the context of the Planck scale, this achievement is almost gentle. The reason lies in how accelerators work. To probe smaller distances, particles must carry higher momentum. Higher momentum requires higher energy. In circular accelerators, like the LHC, particles are bent around a ring by magnetic fields. As their energy increases, they resist bending more strongly. To keep them on track, either the magnetic field must grow stronger or the ring must grow larger. There is no shortcut around this geometry. Superconducting magnets are already operating near their practical limits. Stronger fields would require materials that do not yet exist. That leaves size. If you want to accelerate particles to much higher energies without losing control, the accelerator must grow. At first, this growth feels manageable. Double the energy, double the size. But this intuition breaks down quickly. Each increase in energy demands disproportionate increases in infrastructure, power, and precision. Losses from radiation, especially for lighter particles like electrons, grow rapidly. Stability becomes harder to maintain. Costs rise not linearly, but explosively. Now consider what it would take to reach Planck energy. The Planck energy is roughly a trillion times higher than the energies we routinely achieve in laboratories. To reach it in a circular accelerator using current principles, the ring would need to be unimaginably large, larger than the Earth, larger than the solar system, larger than the Milky Way itself. Even then, the problem would not be solved. Energy is not just something you give to particles, it must come from somewhere. Powering such a machine would require energy outputs rivaling those of stars. Containing and controlling that energy would introduce gravitational effects of its own. The accelerator itself would become a source of space-time curvature. This is where the idea of just build it bigger quietly fails. Linear accelerators face similar constraints. While they avoid the need to bend particles in a circle, they still require enormous lengths to achieve extreme energies. The electric fields used to accelerate particles can only be increased so much before breakdown occurs. Push too hard, and the accelerating structure itself disintegrates. Even advanced concepts such as plasma Wakefield accelerators, which promise higher gradients over shorter distances, run into fundamental limits. They can compress the scale, but not the energy requirement. The total energy needed remains immense. And beyond these engineering challenges lies a deeper obstacle. Even if we could, in principle, construct an accelerator of cosmic proportions, the act of concentrating Planck-scale energy into a small region would trigger gravitational collapse. A microscopic black hole would form. The experiment would end the same way every time. The universe does not reward brute force at this scale. This realization marks a turning point in how physicists think about exploration. The Planck regime is not simply beyond our current reach. It is beyond reach in principle, at least through direct experimentation. The obstacle is not money, materials, or time. It is geometry and gravity. There is something quietly humbling about this. We are used to thinking of the universe as something that yields to cleverness and persistence, and in many ways it does. But here, the rules change. Scale alone cannot solve the problem, because scale itself becomes part of the problem. As accelerators grow, so do their side effects. Energy density, radiation losses, gravitational influence. Each solution introduces new constraints. The system resists simplification. This does not mean the pursuit is meaningless. On the contrary, understanding why no accelerator can be big enough teaches us something essential about reality. It tells us that the universe has built-in thresholds, that certain regimes are protected not by fragility, but by structure. In everyday life, bigger tools often mean better access. A taller ladder reaches higher branches. A stronger microscope reveals finer detail. But at the deepest levels of physics, bigger tools change the environment they are meant to explore. They reshape the very thing they seek to measure. This is why many physicists have shifted focus from direct experimentation to indirect evidence. Instead of trying to recreate Planck scale conditions, they look for traces left behind when such conditions existed naturally. The early universe, for example, may have briefly approached these energies. Subtle patterns in cosmic radiation, gravitational waves, and large-scale structure could carry imprints of Planck-scale physics. This approach requires patience. It replaces the drama of collisions with the quiet work of inference. There is also a philosophical adjustment embedded here. Science has long been associated with control. We isolate variables, we repeat experiments, we demand reproducibility. But the Planck scale resists this framework. It suggests that some aspects of reality can only be approached statistically, indirectly, or mathematically. This does not diminish science, it deepens it. The realization that no accelerator can be big enough does not signal an end. It signals a transition, from direct probing to conceptual understanding, from force to subtlety, from construction to contemplation. As you sit with this idea, notice how it mirrors experiences outside of physics. Some truths cannot be reached by effort alone. Some understanding arrives only when pressure is released. The universe, in its own way, seems to be inviting that shift. And still, curiosity remains. If we cannot reach the Planck regime by building ever larger machines, then how do we approach it at all? That question does not demand an immediate answer. It simply opens the door to the next quiet chapter. Part 8. The collision of quantum mechanics and gravity. Quantum mechanics governs the very small. General relativity governs the very massive. At everyday scales, they coexist peacefully. But at Planck energy, they collide. Quantum uncertainty demands fluctuation, while gravity demands curvature. The equations no longer agree. Our two most successful theories speak different languages, and neither can fully translate the other. To appreciate how deep this conflict runs, it helps to notice how well each theory works on its own. Quantum mechanics describes atoms, electrons, and fields with astonishing accuracy. Its predictions have been tested to more decimal places than any other theory in science. General relativity, on the other hand, explains the motion of planets, the bending of light, and the evolution of the universe itself. It has passed every observational test placed before it. Each theory is complete within its domain. Each is elegant, precise, and deeply reliable. The trouble begins only when their domains overlap. Quantum mechanics is built on uncertainty. At its core lies the idea that certain pairs of properties, like position and momentum, cannot both be known exactly. The more precisely one is defined, the more uncertain the other becomes. This is not a limitation of measurement, it is a feature of reality itself. The quantum world is inherently probabilistic, a sea of possibilities rather than fixed outcomes. General relativity, by contrast, is deterministic in structure. Given the distribution of energy and mass, the curvature of space-time is defined. Objects follow predictable paths through that curved geometry. While chaos can emerge from complex systems, the underlying equations are smooth and continuous. At low energies, these differences do not matter. Quantum fluctuations are tiny. Space-time remains effectively smooth. Gravity is so weak at small scales that it can be ignored. The theories politely stay out of each other's way, but at Planck energy, politeness ends. Quantum mechanics insists that energy fluctuates even in empty space. Fields vibrate. Virtual particles appear and disappear. These fluctuations are small at ordinary scales, but they grow as you probe smaller regions. To examine a tiny volume, quantum mechanics demands a corresponding uncertainty in energy. General relativity responds to energy, not averages. Even fleeting fluctuations curve space-time. When energy uncertainty becomes large enough, the geometry of space and time itself becomes unstable. Tiny curvatures appear and vanish, responding to quantum jitter. The result is a feedback loop neither theory can handle alone. Quantum mechanics assumes a fixed space-time background on which probabilities play out. General relativity assumes a smooth geometry shaped by well-defined energy distributions. At Planck energy, neither assumption holds. Space-time fluctuates, energy fluctuates, geometry and probability become entangled. This is not just a mathematical inconvenience, it is a conceptual impasse. Our best descriptions of nature disagree about what reality is made of at its deepest level. Physicists have tried for decades to reconcile this conflict. Many approaches exist, each attempting to preserve the strengths of both theories while resolving their contradictions. Some propose additional dimensions of space, curled up so tightly they escape detection. Others suggest that space-time itself is quantized, composed of discrete units rather than a continuum. All of these ideas share a common motivation. They arise because the collision of quantum mechanics and gravity demands a new framework. One way to sense the depth of this problem is to consider time. In quantum mechanics, time is an external parameter. It ticks along in the background, unaffected by the systems it describes. In general relativity, time is dynamic. It stretches, slows, and warps depending on gravity and motion. At Planck energy, which version of time is correct? If time fluctuates, how do you define quantum evolution? If time is fixed, how do you account for gravitational effects? The question is not technical, it is foundational. This conflict also touches the nature of space itself. Quantum mechanics treats space as a stage with fixed dimensions. Particles move, fields oscillate, probabilities spread. General relativity treats space as a participant, shaped by what it contains. At the Planck scale, space may be neither fixed nor smooth. It may be something more abstract, emerging from deeper relationships. If so, both theories are approximations, valid only when certain conditions hold. There is something quietly beautiful in this realization. It suggests that our most successful theories are not wrong. They are incomplete. Each captures a facet of reality, but not the whole. As you breathe slowly, let that thought settle. The universe is not obligated to fit neatly into human categories. Our theories are maps, not the territory. And at extreme scales, the map edges fray. The collision of quantum mechanics and gravity also explains why direct experiments at Planck energy are so elusive. The very act of probing this regime would trigger the effects both theories struggle to describe. Energy would fluctuate violently. Space-time would curve unpredictably. The experiment would collapse into the problem it seeks to solve. This is why much of the work toward unification happens on paper rather than in laboratories. Mathematicians and physicists explore consistency, symmetry, and elegance, searching for theories that reduce to quantum mechanics at low energies and to general relativity at large scales. One promising idea suggests that gravity itself may not be fundamental, but emergent. In this view, space-time curvature arises from deeper quantum processes, much like temperature emerges from the motion of atoms. If true, gravity would be a large-scale effect of quantum information, not a force to be quantized directly. Another approach, known as holography, proposes that the physics inside a volume of space can be described entirely by information encoded on its boundary. This idea was inspired by black hole thermodynamics, where entropy scales with surface area rather than volume. It hints that space-time itself may be a projection, not a primary ingredient. These ideas are tentative. They remain incomplete. But they are driven by necessity. The collision of quantum mechanics and gravity demands resolution, even if that resolution lies beyond direct observation. There is a quiet humility in how physicists approach this problem. Rather than forcing nature to conform, they listen for patterns. They test consistency. They accept that progress may be slow and indirect. As this part of the journey draws toward rest, notice how the conflict itself becomes a guide. Where theories disagree, something deeper is hiding. Where equations fail, new principles wait to be discovered. And as we continue onward, another question gently arises. If our theories cannot agree at the deepest level, how do we even define what it means to measure anything at all? Part 9. Why measurement changes the thing. Measured in quantum physics, observation is never passive. To measure is to interact. At extreme energies, this interaction becomes overwhelming. The probe no longer gently reveals structure, it reshapes it. The line between experiment and creation dissolves, leaving us unsure whether we are studying nature or manufacturing it. This idea begins quietly, almost innocently, at the smallest scales. In everyday life, measurement feels harmless. You look at a clock and time continues unchanged. You measure a table and the table remains the same. The act of observing seems separate from the thing observed. Cause and effect feel cleanly divided. But the quantum world does not allow this separation. At microscopic scales, every measurement requires contact. To see an electron, you must scatter something off it. To determine a particle's position, you must exchange energy with it. There is no way to look without touching. And that touch, however gentle, changes the system. This is not a flaw in our instruments. It is woven into the structure of reality. Werner Heisenberg captured this truth in his uncertainty principle. The more precisely you measure a particle's position, the less precisely you can know its momentum. This is not because our tools are crude. It is because position and momentum are linked through the wave-like nature of matter. To pin down one is to disturb the other. At low energies, this disturbance is manageable. The changes introduced by measurement are small. The system remains recognizable. We can repeat experiments and build reliable predictions. Quantum mechanics, despite its strangeness, becomes a precise and practical tool. But as energy increases, the disturbance grows. To probe smaller distances, you must use probes with shorter wavelengths. Shorter wavelengths require higher energy. Higher energy means stronger interactions. At some point, the measurement stops being a gentle question and becomes a forceful intrusion. Imagine trying to learn the structure of a snowflake by striking it with a hammer. The information you gain would be limited, not because the snowflake lacks structure, but because the method of inquiry destroys what you are trying to understand. At extreme energies, something similar happens in physics. The probe does not simply bounce off the system, it reshapes it. In high-energy particle collisions, this is already familiar. When particles collide at enormous energies, they do not merely reveal internal structure. They create entirely new particles. Energy converts into mass, fields rearrange. The outcome is not a snapshot of what was there before, but a new configuration born of the interaction. At Planck scale energies, this effect becomes unavoidable. The act of measurement introduces so much energy into such a small region that space-time itself responds. Geometry bends, horizons form, quantum fluctuations amplify. The system being measured no longer exists independently of the measurement process. This is the point where the classical idea of an experiment breaks down. Traditionally, experiments are designed to isolate variables, to observe without interference. But at the deepest scales, isolation is impossible. The system and the observer are entangled, not just philosophically, but physically. This challenges a deeply ingrained assumption about science, that reality exists independently of our attempts to observe it, and that careful measurement can reveal it without altering its essence. At everyday scales, this assumption works well enough. At extreme scales, it fails. There is something quietly unsettling about this. It suggests that nature does not offer a hidden blueprint waiting to be uncovered. Instead, reality at the smallest scales may be inherently relational, defined by interactions rather than independent objects. Some interpretations of quantum mechanics lean into this idea. They suggest that properties like position, momentum, and even existence itself only take on definite values when measured. Before that, they exist as possibilities, not facts. At low energies, this distinction feels abstract. At high energies, it becomes unavoidable. When the probe reshapes space-time, when black holes form from measurement attempts, when horizons block information, the distinction between observer and observed dissolves completely. The experiment becomes an act of creation. This is why physicists say that at extreme energies, we are no longer studying nature as it is, but nature as it responds to us. This does not mean reality is subjective or arbitrary. It means that interaction is fundamental. Measurement is not a window, It is a process, and every process leaves a trace. There is a quiet parallel here to other areas of knowledge. In psychology, observation can change behavior. In ecology, intervention alters ecosystems. In human relationships, attention itself reshapes dynamics. At the deepest level of physics, the same truth holds. Attention has consequences. As energy rises, those consequences grow until they dominate. This also explains why the Planck scale is not merely difficult to access but conceptually different. At that scale, there may be no meaningful way to separate what is being measured from how it is measured. The universe does not provide a neutral vantage point. Instead, it offers participation. This insight reshapes how physicists think about fundamental questions. Rather than asking, "What is space-time made of?" they begin to ask, "How do interactions give rise to space-time?" Rather than searching for smaller building blocks, they explore relationships, symmetries, and information flow. Some theories suggest that space-time itself emerges from patterns of quantum entanglement. In these views, geometry is not a primary ingredient of reality, but a large-scale manifestation of deeper connections. If true, then trying to measure space-time directly at the smallest scale is like trying to measure the fabric of a dream by pulling on it. The harder you pull, the more it changes. As you rest with this idea, there's no need to resolve it. The discomfort it brings is part of its meaning. It reminds us that knowledge has texture, that understanding is not always about domination or extraction. Sometimes it is about recognizing where our tools no longer apply. This does not diminish science, it deepens it. Science has always advanced by confronting its own limits. Each time a boundary appeared, it revealed not an end, but a transition. The recognition that measurement changes the thing measured is one such transition. It asks us to rethink what it means to know something at all. At extreme energies, the universe does not offer clean answers, it offers feedback. And that feedback is consistent. Push harder, and reality pushes back. Focus energy too tightly, and space-time responds by reshaping itself. Demand finer detail, and the system transforms under scrutiny. There is a quiet wisdom in this. The universe is not fragile, but it is not infinitely accommodating. It allows inquiry, but not invasion. As this part of the journey settles into stillness, one question remains gently suspended. If measurement itself becomes creation, then how do we learn anything at the deepest level without destroying what we seek? That question does not require an immediate answer. It simply guides us onward, deeper into the quiet logic of the cosmos. Part 10. The universe's built-in safety barrier. Some physicists believe the Planck scale acts as a natural firewall, a protective boundary that prevents paradoxes from tearing reality apart. By making space-time unstable at extreme energies, the universe may be enforcing consistency, quietly ensuring that certain questions cannot be answered in destructive ways. At first, the idea of a safety barrier in nature can feel strangely intentional, almost as if the universe were designed with limits in mind. But this is not about purpose or planning. It is about structure, about what happens when fundamental laws intersect and reinforce one another in ways that preserve coherence. Throughout physics, barriers like this appear again and again. The speed of light is one. No matter how much energy you supply, massive objects cannot be accelerated beyond it. This is not a technical inconvenience. It is a structural rule woven into space-time itself. If it did not exist, cause and effect would blur, paradoxes would multiply, the universe would lose its internal logic. The Planck scale may represent a similar kind of boundary, but at the opposite extreme. Instead of limiting how fast information can travel, it limits how finely reality can be resolved. Push beyond a certain point and the rules change. Space-time refuses to remain stable. Measurement becomes impossible. Information hides behind horizons. The universe protects itself from contradictions. This idea arises not from speculation, but from careful reasoning. When physicists attempt to combine quantum mechanics and general relativity at arbitrarily small scales, the mathematics begins to produce infinities. Predictions explode, physical quantities lose meaning. Something is clearly wrong. One response is to assume our theories are incomplete, and they are. But another response is to notice a pattern. Every attempt to push beyond the Planck scale triggers effects that prevent further progress. Energy concentrates, gravity strengthens, space-time fluctuates, black holes form. Each step toward paradox is met with resistance. It is as if reality contains a built-in regulator. This regulator does not forbid curiosity, it redirects it. Instead of allowing infinite precision, it enforces uncertainty. Instead of revealing deeper layers through force, it encourages indirect understanding. In this sense, the Planck scale behaves less like a wall and more like a horizon. You can approach it, you can infer what lies beyond, but you cannot cross it in the usual way. There's something quietly elegant about this arrangement. The same laws that govern stars and atoms also guard against logical collapse. Consistency is preserved not by arbitrary rules, but by the interplay of energy, gravity, and quantum uncertainty. Consider what would happen without such a barrier. If space-time remained smooth at all scales, quantum fluctuations in energy could curve space infinitely. Singularities would be exposed everywhere. Causality could break down. Effects could precede causes. The universe would lose its narrative structure. If, on the other hand, quantum uncertainty did not limit measurement, one could extract infinite information from finite regions. Physical quantities would diverge. Predictions would become meaningless. Again, consistency would fail. The Planck scale sits precisely where these dangers converge. By making space-time unstable at extreme energies, it prevents both scenarios. It blocks infinite precision and infinite curvature from coexisting in observable ways. This does not mean the universe is fragile. It means it is self-consistent. There is a useful analogy here, though it must be held gently. In engineering, safety mechanisms are often designed to fail gracefully. When pressure becomes too high, a valve releases it. When current becomes too strong, a fuse breaks the circuit. These mechanisms do not prevent use, they prevent catastrophe. The Planck scale may serve a similar role in the architecture of reality. When inquiry becomes too invasive, the system responds by changing phase. Smooth space-time gives way to fluctuation, measurement gives way to horizons, information flow slows, then stops. The questions do not disappear, but the methods that produce them are no longer allowed. This perspective reframes frustration as protection. The reason we cannot probe arbitrarily small distances is not because nature is hiding something out of spite, but because unrestricted access would undermine the coherence of everything else. In this light, black holes are not failures of physics, they are stabilizers. They prevent energy from being localized beyond safe limits. They hide singular behavior behind horizons where it cannot disrupt the rest of space-time. Similarly, quantum uncertainty is not a flaw, it is a buffer. It prevents exact knowledge that would allow contradictions to arise. It ensures that certain pairs of properties cannot be simultaneously fixed. Together, these features act as a coordinated system of checks and balances. This idea also sheds light on why so many attempts at unifying physics encounter natural cutoffs. Renormalization procedures introduce energy limits. Effective theories apply only within certain regimes. Each framework works beautifully until it approaches the Planck scale, then gracefully steps aside. Rather than seeing this as failure, some physicists see it as guidance. The universe may be telling us that fundamental understanding does not come from infinite refinement, but from recognizing when refinement no longer applies. That beyond a certain point, reality must be described differently, not measured more aggressively. This resonates with a deeper philosophical shift in modern physics. The focus moves away from particles as tiny billiard balls and toward relationships, symmetries, and information. Instead of asking what exists at the smallest scale, physicists ask how large-scale structure emerges reliably. The safety barrier encourages this shift. It nudges inquiry away from brute force and toward coherence. As you breathe quietly, consider how this mirrors other domains of understanding. In music, sound becomes noise beyond certain intensities. In vision, brightness becomes blindness. In psychology, too much introspection can dissolve clarity. Limits are not always obstacles, they are often guides. The Planck scale may be the universe's way of saying, "Not this way." It does not deny knowledge, it shapes it. We are still free to explore the cosmos, to map galaxies, to probe atoms, to understand forces and fields. The vast majority of reality remains accessible, predictable, and astonishingly well-behaved. The safety barrier appears only at extremes where unrestricted access would threaten coherence. There is something comforting in this restraint. It suggests that the universe values consistency over completeness, stability over total transparency. It allows complexity to flourish without collapsing under its own contradictions. As this chapter gently settles, one thought remains. If the universe enforces limits to protect itself, then perhaps those limits also protect us. They ensure a reality that can be explored, inhabited, and understood without unraveling. And as we continue this quiet journey, another question begins to rise. If direct answers are blocked by design, then what indirect paths remain open to us? Part 11. Why time itself becomes unclear. As energy increases, time behaves strangely. At relativistic speeds, it slows. Near intense gravity, it stretches. At the Planck scale, time may lose its meaning entirely. The familiar flow from past to future may dissolve into something more abstract, where cause and effect blur into probabilities. To feel how unsettling this is, begin with how dependable time seems in everyday life. Seconds pass evenly. Clocks agree closely enough. Morning follows night with gentle regularity. Even when days feel long or short, the underlying rhythm remains steady. Time feels like a quiet river, flowing in one direction, carrying everything with it. Physics, however, has taught us that this river is not as uniform as it appears. Einstein's theory of relativity was the first major shift. It revealed that time does not flow at the same rate everywhere. Motion and gravity affect it. Move fast enough, and your clock ticks more slowly compared to someone at rest. Fall deeper into a gravitational field, and time stretches further. These are not metaphors. They are measurable effects, confirmed by atomic clocks on airplanes and satellites. At these scales, time remains understandable. It stretches, but it still flows. Past, present, and future remain distinct, even if they no longer align perfectly between observers. But as energy increases further, the picture grows less stable. In quantum mechanics, time plays a very different role. It is not something that fluctuates or bends. It is treated as an external parameter, a background against which change is measured. Quantum systems evolve with respect to time, but time itself is not part of the quantum system. It does not jitter, it does not blur, it simply ticks. This difference is usually manageable. For atoms and particles, gravity is negligible. For planets and stars, quantum effects average out. Time can wear two faces without conflict. At the Planck scale, those faces collide. Here, energy densities are so high that space-time itself fluctuates. Geometry becomes uncertain, distances blur, and because time is woven inseparably into space-time, it too begins to lose definition. If space flickers, so must time. If geometry is uncertain, so is sequence. This leads to a profound question. What does it mean to speak of before and after when time itself fluctuates? At the Planck scale, the notion of a smooth timeline may no longer apply. Events may not be ordered in a simple sequence. Cause and effect may not be sharply defined. Instead of a single history, there may be overlapping possibilities, branching and recombining in ways our ordinary intuition cannot grasp. This does not mean that time vanishes completely. It means that our familiar concept of time may be an approximation, valid only when fluctuations average out. Consider temperature as an analogy. At the scale of individual molecules, temperature is not well defined. Molecules move at different speeds. Only when you consider large numbers do averages emerge. Temperature becomes meaningful not as a property of a single particle, but of a collective. Time may be similar. At very small scales, it may not exist as a smooth parameter. Only when many quantum processes are considered together does a stable flow emerge. Some physicists suggest that time is not fundamental at all, that it emerges from change, from relationships between states, rather than existing independently. In this view, there is no universal clock ticking beneath reality. There are only correlations, patterns of change that give rise to the sensation of flow. At everyday scales, these patterns align so consistently that time feels absolute. At extreme scales, they may fragment. This idea challenges deeply held assumptions. We are used to thinking of time as the backdrop against which everything happens. But at the Planck scale, there may be no backdrop, only interaction. This helps explain why attempts to define time precisely at extreme energies run into paradoxes. If you try to measure a very short time interval, you must use a probe with very high energy. That energy curves space-time. It alters the duration you are trying to measure. The act of defining time changes it. Once again, measurement reshapes the system. This also complicates the idea of causality. In everyday life, causes precede effects. This ordering feels absolute, but in relativity, simultaneity already depends on the observer. Events that are simultaneous in one frame may not be in another. At high energies and strong gravity, even this ordering becomes unstable. At the Planck scale, where space-time fluctuates violently, causal order may become probabilistic rather than fixed. Events may not have a single, well-defined sequence. Instead, multiple causal paths may coexist, with probabilities assigned rather than certainties. This does not mean the universe becomes nonsensical. It means it operates under rules that do not privilege a single timeline. There is a quiet resonance here with quantum mechanics itself. In the quantum world, particles do not follow single trajectories. They explore many possibilities at once. Only when measured do outcomes crystallize. Time, at the deepest level, may behave similarly. This has led some physicists to propose that the arrow of time, the sense of direction from past to future, emerges only at large scales. It may arise from entropy, from the tendency of systems to move from ordered to disordered states. At the Planck scale, where entropy itself may not be well defined, the arrow may blur. The early universe offers a hint of this. Near the Big Bang, energy densities were enormous. Space-time curvature was extreme. Time, as we understand it, may not have existed in the same way. The question, what happened before the Big Bang, may not be meaningful, not because the answer is hidden, but because before may not apply. This realization can feel unsettling, even disorienting. We rely on time to structure experience, to plan, to remember, to make sense of change. The idea that time itself might dissolve at the deepest level challenges not just physics, but intuition. And yet, there is also calm here. The time you experience now is stable because the conditions around you are stable. Energy densities are low. Space-time is smooth. Quantum fluctuations average out. The arrow of time points clearly forward. Nothing in this deep uncertainty threatens that everyday flow. Instead, it explains it. The clarity of time at human scales may be a gift of distance, of scale, of being far from extremes. Just as the surface of the ocean appears calm from afar, time appears smooth because we are not close enough to its underlying turbulence. As this part of the journey settles, notice how the universe once again invites humility. It does not promise absolute foundations. It offers reliable patterns where life can exist and curiosity can rest. And at the edges, it softens certainty into possibility. If time itself becomes unclear at the deepest level, then perhaps our questions must become gentler there as well. Less about exact sequences, more about relationships. Less about moments, more about structure. And as we drift onward, one final thought emerges quietly. If time dissolves into probability at the smallest scales, then how does the steady flow we experience arise at all? That question will guide the next chapter of this calm exploration. Part 12. The early universe as a natural experiment. The only place Planck energies may have truly existed is at the very beginning of the universe. In the first instant after the Big Bang, everything was compressed, energetic, and unstable. The universe itself ran the experiment we cannot repeat, leaving behind only faint echoes in cosmic structure and radiation. To imagine this moment, it helps to release the picture of an explosion happening at a point in space. The Big Bang was not a blast within the universe, it was the universe. Space, Time, energy, and matter all emerged together, expanding from an initial state of extreme density. There was no surrounding darkness, no empty stage waiting to be filled. The stage itself was unfolding. In those earliest moments, the conditions were unlike anything that exists today. Temperatures were unimaginably high. Energy densities approached the limits defined by the Planck scale. Forces that are now distinct, gravity, electromagnetism, and the nuclear forces, may have been unified, behaving as a single interaction. The universe was not calm. It was not structured. It was raw. And yet, it was lawful. This is what makes the early universe such a valuable natural experiment. It reached energies we cannot create, explored regimes we cannot access, and did so according to the same fundamental principles that govern reality now. The universe did not violate its own rules. It revealed them. For a fleeting instant, far shorter than any time interval we can meaningfully define, Planck-scale physics may have dominated. Space-time itself may have fluctuated violently. Quantum uncertainty and gravity would have been inseparable. Geometry may not have been smooth. Time may not have flowed in a familiar way. Then, as the universe expanded, everything cooled. Energy densities dropped, forces separated. Space-time settled into a more stable form. The wild fluctuations of the earliest moments smoothed out, leaving behind subtle imprints rather than direct evidence. The experiment ended almost as soon as it began, but its results were frozen into the structure of the cosmos. Today, we search for those results. One of the most important relics of the early universe is the cosmic microwave background, a faint glow of radiation that fills all of space. It is the cooled remnant of a time when the universe was hot and opaque, when light could not travel freely. As the universe expanded and cooled enough for atoms to form, light was released, carrying with it a snapshot of conditions from nearly 13.8 billion years ago. This radiation is astonishingly uniform. Everywhere we look, it has nearly the same temperature. This uniformity tells us that the early universe was remarkably smooth. But it is not perfectly smooth. Tiny variations exist, differences of only 1 part in 100,000. Those tiny variations matter. They represent the seeds of everything that followed. Galaxies, clusters, stars, and planets all grew from these faint irregularities. Gravity amplified them over billions of years, turning subtle ripples into vast structures, and those ripples may carry echoes of Planck-scale physics. Some of the variations in the cosmic microwave background are thought to originate from quantum fluctuations stretched to cosmic scales during a brief period of rapid expansion known as inflation. If this picture is correct, then the largest structures in the universe began as quantum events at the smallest scales. The universe itself became the amplifier. Inflation smoothed out irregularities while preserving tiny quantum fluctuations, magnifying them into the patterns we observe today. In this way, Planck-scale uncertainty may have left fingerprints across the sky, visible not through direct measurement, but through statistical patterns. This is a recurring theme. The early universe does not give us sharp images of Planck-scale physics. It gives us shadows, distributions, correlations, echoes. Gravitational waves offer another possible window. Ripples in spacetime generated by violent processes in the early universe may still be traveling through space today. If detected, they could carry information about energy scales far beyond anything we can produce in laboratories. These signals are extraordinarily faint. Detecting them requires patience and precision, but they represent a different approach to experimentation. Instead of recreating extreme conditions, we listen for the aftermath. There is something quietly poetic about this. The universe ran its most extreme experiments before there were observers to witness them. Now, billions of years later, we sift through the debris, piecing together stories from faint clues left behind. This method requires humility. We must accept that our access to the deepest physics is indirect. We reconstruct, infer, and model rather than observe directly. But this does not make the knowledge less real. It makes it more delicate. The early universe also reminds us that Planck-scale physics is not something alien or separate from the cosmos we inhabit. It is part of our history. Every atom in your body traces its lineage back to that initial state. The laws that governed the universe then are the same laws that govern it now. What changed were the conditions. As expansion continued, energy diluted, space-time stabilized. The safety barriers we have discussed emerged naturally. The universe transitioned from a regime where Planck scale effects mattered everywhere to one where they are hidden deep beneath layers of scale. This transition may itself hold clues. How did space-time become smooth? How did time acquire a clear direction? How did gravity settle into its familiar form? These questions are not abstract. They are written into the large-scale structure of the universe. In this sense, the early universe is not just a past event, it is an ongoing reference, a baseline against which all later evolution is measured. There's also a quiet reassurance here. The fact that the universe survived its own extremes suggests resilience. Whatever the Planck scale regime was like, it gave rise to a cosmos capable of cooling, organizing, and sustaining complexity. The wildness of the beginning did not persist. It transformed. As you rest with this thought, notice how it reframes our limitations. We cannot reach Planck energies now, not because we are too late or too small, but because the universe itself has moved on. It expanded into a gentler phase where life and observation are possible. In that gentler phase, curiosity thrives. We may never directly witness the Planck era, but we can understand its consequences. We can trace patterns backward. We can test consistency. We can listen to the universe's memory. This is not a lesser form of knowledge. It is a different one. As this chapter comes to a quiet pause, one question remains softly open. If the early universe explored the deepest physics on our behalf, then what other clues might still be waiting, hidden in plain sight across the cosmos? That question carries us gently forward into the next part of this unfolding story. Part 13. Why theory replaces experiment at the edge. When experiments become impossible, physics does not stop. It changes shape. Mathematics, symmetry, and internal consistency take over where instruments cannot go. Theories of quantum gravity, string theory, and loop quantum gravity attempt to describe what cannot be tested directly, guided by logic rather than measurement. For much of scientific history, progress followed a familiar rhythm. Observation inspired theory. Theory guided experiment. Experiment refined understanding. This cycle was steady, reliable, and deeply satisfying. When predictions were confirmed, confidence grew. When they failed, theories were revised or abandoned. At the edge of the Planck scale, this rhythm slows. Here, experiments cannot reach. Energy requirements become prohibitive. Measurement reshapes the system. Horizons hide information. The universe places a quiet boundary around direct testing. And yet, the desire to understand does not fade. It adapts. In these regimes, theory becomes the primary tool. This does not mean imagination replaces rigor. On the contrary, theoretical physics at the edge demands extraordinary discipline. Without experimental correction, ideas must be constrained by mathematical consistency, by agreement with known physics, and by internal coherence. A theory that contradicts itself is discarded, no matter how elegant it appears. Mathematics becomes both the language and the filter. Symmetry plays a central role. Throughout physics, symmetries have guided discovery. Conservation laws arise from them. Forces reveal themselves through them. When direct observation is impossible, symmetry becomes a compass, pointing toward structures that are stable and self-consistent. This is why many approaches to quantum gravity begin by asking what symmetries space-time should possess at the deepest level. Should they resemble those we see at large scales, or break in subtle ways? How do they behave when geometry itself fluctuates? String theory is one response to these questions. It replaces point-like particles with tiny vibrating strings. In this framework, particles are not fundamental objects, but different vibrational modes of a deeper entity. Gravity emerges naturally as one of these modes, unifying it with other forces within a single mathematical structure. What makes string theory compelling is not direct evidence, but consistency. It avoids certain infinities. It incorporates quantum mechanics and gravity without obvious contradiction. It suggests new symmetries and dimensions that resolve mathematical tensions. Loop quantum gravity takes a different path. Instead of introducing new dimensions or entities, it focuses on quantizing space-time itself. In this view, space is composed of discrete units woven into networks. Geometry is granular, not continuous. Time evolves through changes in these networks rather than flowing smoothly. Both approaches are attempts to respect what we already know while extending it into regimes we cannot test. They are guided by logic rather than data, by necessity rather than convenience. This shift can feel unsettling. Science is often celebrated for its empirical grounding. Experiments are its anchor. When theory moves ahead without experimental support, skepticism naturally arises. But history offers perspective. Before telescopes could resolve planetary motion precisely, mathematics predicted their paths. Before radio waves were detected, equations described their existence. Before atoms were observed directly, their behavior was inferred from patterns in chemistry and thermodynamics. Theory has often led the way when technology lagged behind. The difference at the Planck scale is not just technological delay, it is fundamental limitation. Experiments may never reach this regime directly. If understanding is to progress, it must do so through reasoning. This reasoning is not free form. Theories must reduce to known physics at accessible scales. They must reproduce the successes of quantum mechanics in general. Relativity, where those theories are known to work. Any deviation must be subtle, emerging only under extreme conditions. This constraint is powerful. It narrows the field of viable ideas. There is also an aesthetic dimension here, though it is not superficial. Physicists speak of elegance, simplicity, and beauty, not as decoration, but as signals of coherence. The universe has repeatedly shown that deep laws are simple at their core, even if their consequences are complex. When theory replaces experiment, beauty becomes a clue. This does not guarantee truth. Many beautiful theories have been wrong, but ugliness, inconsistency, and arbitrariness rarely survive scrutiny. As you rest with this thought, notice how different this mode of exploration feels. There are no collisions, no detectors flashing. Instead, there are equations, patterns, and quiet debates. Progress is slower, validation is indirect, patience is essential. This patience reshapes the culture of physics itself. Collaboration becomes crucial. Ideas are tested against one another for consistency rather than against immediate data. Theoretical frameworks evolve gradually, refined by critique and comparison. This does not mean theory floats unmoored from reality. It remains anchored by what we know. It must explain why the universe behaves as it does at accessible scales. It must account for black holes, cosmic expansion, and quantum phenomena without contradiction. In this way, theory becomes a bridge rather than a replacement, a bridge between what can be measured and what must be inferred. There is also humility here. Physicists recognize that current theories may be incomplete or even wrong. They are provisional maps drawn where direct surveying is impossible. They guide exploration, but they do not claim finality. This humility aligns with the broader theme of this journey. The universe does not yield its deepest truths easily. It invites careful listening rather than forceful probing. As you breathe quietly, consider how theory itself becomes a form of observation, not of phenomena, but of possibility. It explores what could exist without violating what already does. It charts landscapes of consistency, marking regions where reality could safely reside. This is not a retreat from science. It is an expansion of it. At the edge, physics becomes contemplative. It balances creativity with restraint. It accepts that some answers may remain indirect, encoded in patterns rather than revealed through direct inspection. And yet, even here, experiment does not disappear entirely. Indirect tests remain possible. Cosmological observations, gravitational waves, and subtle deviations from known laws may one day point toward or away from certain theories. The dialogue between theory and observation continues, just on quieter terms. As this chapter settles into stillness, one thought remains gently unresolved. If theory must guide us where experiment cannot follow, then how do we know when we are moving closer to truth rather than deeper into abstraction? That question does not demand an immediate answer. It simply prepares the ground for the final steps of this calm exploration. Part 14. What the Planck limit teaches us about knowledge. There is something quietly humbling about a universe with hard limits. Not every question can be answered experimentally. Not every scale can be reached. The Planck energy reminds us that understanding is not the same as control, and that mystery is not a failure of science, but a feature of it. For much of human history, knowledge felt like conquest. Each discovery pushed the boundary outward. Each new tool peeled back another layer of ignorance. Fire, writing, telescopes, microscopes, engines, computers. Progress appeared linear, almost inevitable. With enough effort, it seemed, any secret could be uncovered. Modern physics gently complicates that story. The Planck limit does not announce itself with drama. It does not forbid curiosity or halt progress. It simply waits, silent and immovable, reminding us that some questions change when you push them too far, that the act of inquiry itself can alter the conditions under which answers exist. This is not a defeat, it is a lesson. Science has always thrived on limits. Absolute zero taught us about thermodynamics. The speed of light taught us about relativity. The uncertainty principle taught us about the quantum nature of reality. Each limit refined our understanding rather than restricting it. The Planck scale belongs to this tradition. It tells us that reality is structured, not infinitely pliable. At everyday scales, control feels natural. We can manipulate matter, guide energy, and predict outcomes with remarkable accuracy. These successes are real and profound. They form the foundation of technology, medicine, and modern life. But they also shape our expectations. We begin to equate understanding with mastery. The Planck limit invites a quieter perspective. It suggests that understanding can exist without domination. That knowledge can be deep even when access is indirect. That inference, consistency, and pattern recognition are as valid as direct measurement. This shift is subtle, but important. When physicists realized that Planck energies could not be reached experimentally, the response was not despair, but adaptation. The focus turned inward, toward theory, toward cosmology, toward indirect evidence. The questions did not disappear. They evolved. What is space-time made of? How does gravity emerge? Why does time flow? These questions remain alive, even if they cannot be answered by smashing particles together harder and harder. This teaches us something about the nature of scientific inquiry itself. Science is not merely a method for extracting answers. It is a dialogue with reality. And like any dialogue, it involves listening as much as speaking. The universe speaks through patterns, through regularities, through constraints. When it finally resists certain kinds of questions, it may be guiding us toward better ones. There is also a deeper philosophical lesson here, one that reaches beyond physics. Human curiosity often assumes that the world owes us explanations in forms we prefer. Clear, direct, repeatable. But the Planck limit reminds us that nature is not obligated to be fully transparent. It is only obligated to be consistent. Consistency, in this sense, is more fundamental than accessibility. The universe allows itself to be understood well enough for life to exist and intelligence to emerge. It offers stable laws, reliable patterns, and discoverable structure. But it does not offer infinite resolution. It preserves mystery at its foundations, not as an oversight, but as an outcome of its architecture. This challenges a common misunderstanding of science. That mystery is a temporary gap, waiting to be filled. In many cases, mystery is not a lack of knowledge, but a boundary condition. The Planck scale marks such a boundary. It tells us that the smallest scales may not be meaningful in the way we expect, that space and time themselves may be emergent rather than fundamental. That asking what lies beneath them may be like asking what lies north of the North Pole. The question itself may lose coherence. This does not mean there is nothing there. It means our language, shaped by larger scales, may no longer apply. There is a quiet maturity in recognizing this. Science, at its best, is not about forcing answers from an unwilling universe. It is about refining questions until they align with how reality actually behaves. The Planck limit sharpens that alignment. It forces us to distinguish between questions that are physically meaningful and those that arise from extrapolating intuition beyond its domain. As you rest with this idea, notice how it softens the relationship between knowledge and certainty. Understanding does not require absolute answers. It requires coherence, consistency, and humility. This humility is not resignation. It is clarity. The universe we inhabit is vast, ordered, and deeply intelligible at many levels. The fact that it contains limits does not diminish its beauty. It enhances it. It suggests that reality is not a blank slate, but a carefully balanced structure where freedom and constraint coexist. Even within these limits, discovery continues. We map galaxies, detect gravitational waves, image black holes, and decode the chemistry of distant worlds. None of this is slowed by the Planck scale. Instead, it is framed by it. We know where direct access ends and where inference must begin. This framing protects science from overreach. It keeps speculation grounded. It reminds us that not all unknowns are equal. Some are open frontiers, others are horizons. There is also a personal resonance here. In everyday life, limits are often experienced as frustrations, physical limits, emotional limits, cognitive limits. We are taught to overcome them, to push past them, to treat them as obstacles. Sometimes that is necessary, but sometimes limits are informative. They tell us where effort should change direction. The Planck limit is a cosmic example of this principle. It does not say, "Do not ask." It says, "Ask differently." Instead of demanding direct access to the smallest scales, we look for emergent behavior. Instead of isolating points in space-time, we study relationships. Instead of insisting on absolute precision, we embrace probabilistic structure. This approach has already reshaped physics. Concepts like entropy, information, and entanglement now play central roles in understanding gravity and space-time. These ideas do not require Planck-scale experiments to be meaningful. They require careful reasoning and subtle observation. In this way, the Planck limit enriches knowledge rather than constraining it. It reminds us that science is not a ladder that climbs endlessly upward, but a landscape with ridges, valleys, and horizons. Progress involves navigation as much as ascent. As this chapter gently comes to rest, there is a quiet reassurance to hold on to. The universe is not withholding its deepest truths out of secrecy. It is offering them in forms that respect coherence, stability, and meaning. Mystery here is not ignorance, it is structure. And as we prepare to take the final step of this journey, one last thought begins to settle. If limits shape understanding rather than end it, then perhaps the greatest insight the Planck scale offers is not about energy or space-time, but about how to know anything at all. Part 15. Resting at the edge of what can be known. At the end of this journey, we find not frustration, but stillness. The Planck energy stands as a quiet horizon, marking where our current understanding gently fades. Beyond it may lie deeper order or deeper mystery. For now, the universe asks us to pause, to observe from a distance, and to accept that some boundaries exist, not to stop curiosity, but to give it shape. It is natural, after traveling so far into the foundations of reality, to expect a final revelation, a hidden mechanism, a smallest piece, a definitive answer waiting just beyond reach. But the lesson of the Planck scale is softer than that. It does not end with a solution, it ends with perspective. Throughout this exploration, we have followed energy as it grows more intense, more concentrated, more disruptive. We have seen how it bends space, distorts time, triggers gravity, and eventually closes off access through horizons. Each step inward revealed not just new physics, but new limits, not imposed from outside, but arising naturally from the structure of the universe itself. At the Planck energy, those limits converge. Here, space-time no longer behaves like a calm backdrop. Measurement ceases to be gentle. Time loses clarity. Geometry trembles. Our most powerful theories speak past one another. And rather than forcing an answer, reality seems to whisper the same message again and again. Slow down. This is not the silence of ignorance. It is the silence of balance. In everyday life, stillness often feels like absence, a lack of motion, a pause between actions. But in physics, stillness can be rich with meaning. Uniform motion feels like rest. Equilibrium hides immense activity beneath its surface. The vacuum itself is alive with fluctuation. The Planck horizon carries this kind of stillness. Beneath it, something is happening. But it is happening in a way that resists direct intrusion. There is a temptation to see this as a defeat for science, as if reaching a boundary somehow diminishes our progress. But the history of understanding tells a different story. Every meaningful advance has come not from ignoring limits, but from recognizing them. When astronomers realized that stars were not fixed points, but distant suns, perspective changed. When physicists realized that time and space were relative, understanding deepened. When quantum mechanics revealed uncertainty at the heart of matter, knowledge expanded rather than collapsed. The Planck scale belongs to this lineage. It does not close the book, it changes the language. Instead of asking what lies beneath space-time, we begin to ask how space-time arises. Instead of demanding direct access to the smallest scales, we look for consistency across scales. Instead of treating mystery as a problem to be eliminated, we treat it as a clue. This shift is subtle but profound. It invites a kind of intellectual rest, not a stopping of thought, but a release of strain. The realization that not every answer must be extracted by force allows curiosity to soften into contemplation. As you sit quietly now, breathing gently, consider how different this feels from conquest. The universe is not something to be overcome. It is something to be understood on its own terms. The Planck horizon reminds us that understanding does not require infinite reach. It requires coherence, theories that agree with one another, observations that align across scales, patterns that persist even when details remain hidden. In this sense, the deepest truths may not be found at the smallest distances, but in the relationships that hold across vast ones. The same constants that define the Planck scale govern stars and atoms alike. The same principles that limit measurement give rise to stable structures. The same uncertainty that blurs the deepest level allows creativity, complexity, and life to emerge at higher ones. Nothing about this boundary is hostile, it is protective. By preventing infinite concentration, the universe avoids tearing itself apart. By limiting precision, it preserves consistency. By hiding certain regimes behind horizons, it ensures that cause and effect remain meaningful. The world you inhabit exists because these limits exist. This is easy to forget when thinking in abstract terms. But without these boundaries, space-time might never have stabilized. Time might never have flowed in a clear direction. Matter might never have clumped into stars, planets, or people. The Planck scale is not separate from everyday life. It is part of the foundation that makes everyday life possible. And so, resting at this edge is not resignation. It is gratitude. Gratitude for a universe that allows understanding without demanding domination. Gratitude for laws that are deep but not destructive. Gratitude for mystery that invites wonder rather than despair. There is also something deeply human in this moment. Curiosity does not disappear when it reaches a horizon. It changes posture, it becomes patient, it learns to infer rather than grasp, to listen rather than demand. This is how astronomy learned about black holes long before imaging them. This is how quantum mechanics predicted particles decades before they were detected. This is how cosmology reconstructs the early universe from faint radiation. The same will be true for whatever lies beyond the Planck horizon. If deeper order exists there, it will leave traces, subtle patterns, constraints that ripple outward into the scales we can observe. We will not be blind to it. We will simply not touch it directly. There is a calm dignity in that. As this journey settles, imagine standing at the edge of a vast ocean at night. You cannot see its depths, you cannot map its floor, but you can hear its rhythm, you can feel its presence, you can know that it is there without crossing into it. The Planck scale is like that ocean, vast, quiet, and deep, not empty, not unreachable, just beyond the tools we currently hold. And for now, that is enough. Science continues, curiosity remains alive, new ideas form, new connections emerge. Their success will not be measured by how far they push past the boundary, but by how gracefully they align with everything on this side of it. As you rest here, let that thought settle gently. You do not need to resolve the deepest mysteries to be part of a meaningful universe. Understanding grows not only through answers, but through respect for structure. The Planck horizon stands not as an ending, but as a place to pause, to breathe, to look outward again, carrying with you the quiet knowledge that reality is deeper than reach, richer than control, and calmer than we often expect. And in that stillness, curiosity does not fade, it rests. As this quiet journey comes to a close, nothing has truly ended. We have simply reached a place where questions soften, where curiosity rests without needing to push forward. The Planck energy remains there in the distance, not as a wall, but as a horizon, a gentle reminder that the universe is deeper than our reach, and yet generous in what it allows us to know. Tonight, you've drifted through ideas larger than galaxies and smaller than time itself. You've followed energy as it bent space, blurred time, and finally asked us to slow down. And in doing so, the universe offered something rare. Not answers, carved in certainty, but balance, structure, quiet consistency. There is comfort in knowing that reality is not fragile, that it protects itself, that the same laws which limit our reach also allow stars to shine, time to flow, and life to exist in calm continuity. The boundaries we explored are not failures of understanding. They are part of the architecture that makes understanding possible at all. As you rest now, there is nothing left to solve, no mystery that demands effort. The universe does not require you to reach its deepest layer to belong within it. You are already carried by its rhythms, moving gently through space and time, supported by laws older than memory. If this calm exploration brought you even a small sense of peace, I'm deeply grateful you chose to spend this time here. Your presence, your quiet attention, means more than words can hold. For now, let your thoughts settle. Let the questions fade into stillness. The universe will continue turning, steady and patient, whether we watch or sleep. And so may you rest as well.